Okay, hello everyone. Thank you for joining the webinar. Let's go ahead and get started. My name is Mark Bollinger, and I'm a research scientist with the Lawrence Berkeley National Laboratory. I'm joined today by my Berkeley Lab colleagues and co-authors, Will Gorman and Dev Milstein, and the purpose of today's webinar is to run through the contents of a journal article that we, along with Dirk Jordan from NREL, have recently published in the Journal of Renewable and Sustainable Energy. And the title of that article is System-Level Performance and Degradation of 21 Gigawatts of Utility-Scale PV Plants in the United States. Just a few quick announcements before we get going. First, this webinar will run for just half an hour, so the presentation will be relatively brief, followed by a few minutes for questions. So if you do have any questions, please submit them by clicking on the Q&A button that you should see somewhere on your screen. So we'd prefer that you use the Q&A function as opposed to the chat function, and we'll try to get through as many of those as we can. The webinar is being recorded, and within a few days will be posted to the same Berkeley Lab website where you can find the open access journal article, and I will provide a link to that web page on the last slide. Okay, here's a quick overview of what I'll cover. I'll introduce the topic by trying to convince you why this matters, and then I will take a minute to draw the distinction between system-level performance decline and module-level degradation. We're measuring the former, not the latter, and it's important to keep that in mind as you digest our findings. Then I'll briefly describe the data sample before getting into our approach and findings for our assessment of both first-year performance as well as project performance decline over time. And then we should have a few minutes at the end for Q&A. So understanding utility-scale PV system performance is important because utility-scale projects, which we define here to include any ground-mounted project that's larger than 5 megawatts of AC capacity, these projects make up the bulk of the overall solar market in the United States. Yet the utility-scale sector is still relatively young. The first utility-scale PV plants in the U.S. came online as recently as 2007. So that's not a long track record, particularly for a technology that is expected to operate for 30 years or longer. And while the first few projects date back to 2007, the market has been growing very rapidly in recent years, which means that the average utility-scale PV project in the U.S. is really only a few years old at this point. And this combination of a young market supplying the bulk of solar energy in the U.S. makes understanding how these projects are performing paramount. This is particularly true given the ongoing phase down of the federal investment tax credit, which elevates the importance of solid performance in order to meet return targets. And likewise, as both the price and duration of power purchase agreements, or PPAs, continue to decline, there is increasing focus on long-term performance and reliability during the post-PPA period. Now, much of the PV performance literature to date has focused on module-level performance and degradation, and that is certainly understandable given that the module is, of course, the backbone of the system. But what truly impacts the bottom line for investors and project owners is total system performance, and that's what our work here focuses on. And I want to draw that distinction a little more clearly on this next slide. The graph here shows an illustrative, stylized buildup from module-level degradation to system-level performance decline over time. So the dark blue shaded area or wedge that you see up top of the graph shows the contribution of module degradation, which in this example is running at around 0.5% per year, as you can see from the right-hand y-axis. The vertical bars in the graph that kind of drop down from the top show isolated hypothetical loss events related to different balance of system components, while the correspondingly colored shaded areas or wedges track the cumulative loss over time resulting from these isolated events. So for example, failures of inverters or breakers or transformers might knock the entire plant offline for some period, while other things like misaligned and stuck trackers or maybe curtailment, those might cut only part of the plant's output at certain times. But all of these individual events contribute to cumulative performance loss over time, which, as you can see over on the right-hand y-axis, is running at around 1.3% per year in this example, and that's more than twice as much as module degradation alone. So please do keep this distinction in mind as we run through this. Namely, we're looking at system-level performance decline and not just module degradation. Okay, I'll just briefly describe the project sample. We looked at 411 utility-scale PV projects totaling 21 gigawatts of DC capacity installed across 28 states from 2007 through 2016. And this means that we've got anywhere from 2 to 11 years of operational history for each plant. In aggregate, the plants in our sample contributed more than half of all solar generation in the United States in 2017, and that's across all three sectors, residential, commercial, industrial, and utility scale. So it's a pretty big chunk of the overall market that we're looking at here. Not surprisingly, the sample tends to be dominated by California and other southwestern states, though again, the full sample does span 28 states. Here we see a bit more of a sample description, in this case focusing on trends over time in the table at the top, as well as the distribution of plant size or plant capacity in the histogram at the bottom. In the table, you can see a progressively larger or growing sample in recent years, featuring larger projects with higher DC to AC ratios and greater use of single-axis tracking. The histogram, meanwhile, shows that many projects fall into the 20 to 50 megawatt size range, but we do also have some very large projects in our sample as well, upwards of several hundred megawatts. And for each project in the sample, we collect key information required for the analysis. So this includes project characteristics, often referred to as metadata, and we were fortunate here to be able to draw upon our extensive project-level database that we've compiled for our annual utility-scale solar report series, which is a parallel effort that's also funded by the Department of Energy's Solar Energy Technologies Office. We also collected net generation data for each project from the various sources listed here. And though we came into this project hoping to be able to use higher resolution data, for example, at least monthly resolution data, in the end, due to some data quality issues that I won't get into here, we were forced to use annual calendar year performance data. And this does impose some limitations on what we're able to do. The flip side, though, is that annual generation data are publicly available and easily obtainable, which enables analysis of a larger sample of projects. For each project site, we pulled irradiance data from 2008 through 2018 from the National Solar Radiation Database, or NSRDB. And finally, we did attempt to control for curtailment within CAL-ISO and ERCOT, which at present are the only two ISOs to report solar curtailment data. And we used all of these data to calculate both actual and idealized or ideal capacity factors for each project. So in other words, we normalized performance across all projects by calculating annual calendar year capacity factors using the formula shown at the bottom of this slide. Okay, moving on to our findings. We assessed first-year project performance in two ways. On the left, for the full sample, we compared irradiance normalized actual first-year capacity factors, which are shown here on the y-axis, to modeled TMY, or typical meteorological year capacity factors, along the x-axis. And as you can see, the correlation is pretty good at 93%. There is slight underperformance in the median, but these results do tend to be largely consistent with past studies that have looked at smaller samples. The graph on the right makes the same comparison, but in this case to stated performance expectations as revealed or gleaned from power purchase agreements. So the sample here on the right is considerably smaller given the scarcity of publicly available PPA documents. And the correlation here is not as good. There's more of a scatter. But at the same time, there does not seem to be any systematic bias in one direction or the other And in this case, we see a slight overperformance relative to stated expectations. So in general, at least based on these two graphs, there doesn't seem to be a systematic reason for concern regarding first-year project performance. But how does performance hold up in later years? To answer that question, we used what's known as a fixed effects regression model, and here I thought I'd briefly define the terms of that equation. So the left-hand variable here that you see in purple is the actual capacity factor using the raw empirical data, and for plants located in California and Texas, we gross up the actual capacity factor to correct for curtailment. The first variable on the right-hand side, shown there in blue, is called the ideal capacity factor, which is modeled based on the plant characteristics or metadata as well as the solar resource. And the basic idea behind this idealized or ideal capacity factor is to control for as much of the geographic and temporal variability in capacity factor as we can by modeling how the project should have performed based on its metadata and solar resource. Then next in green, we have the site-level fixed effects variable, SF, whose purpose is to control for any remaining difference across projects or sites that are not already captured by the ideal capacity factor. Likewise, in red, we have the age fixed effects variable, AT, whose purpose is to control for any remaining variation within each plant over time that, again, is not already captured by the ideal capacity factor. And this age fixed effects variable is really what we're focusing on, as it will tell us how the average fleet-wide performance has changed with project age. Now, sticking with equations just for one more minute here, this regression is called a fixed effects model because it holds constant or fixes the average effects of each variable in the equation. And we can illustrate how this works through two simple transformations of the original equation 1 that's shown up top and that I just walked you through on the previous slide. So equation 2 here simply takes the average of each variable in equation 1 over time, and because the site-level fixed effects SF do not vary over time, the average of SF is simply equal to itself, or SF. And then equation 3 towards the bottom simply subtracts equation 2 from equation 1. As you can see, the site-level fixed effects, or SF, cancel out and drop out of the equation, leaving only those explanatory variables that actually vary over time. So in other words, by subtracting the means, we eliminate all unobservable variation across plants and leave only the variation within plants over time, which is exactly what we're interested in. Okay, here we see the results of the model. The blue dots represent the age fixed effects for each age 1 through 11. The shaded blue area represents the 95% confidence interval around those age fixed effects. And you can see that the confidence interval widens out quite a bit as sample size declines for ages 8 through 11. And then the blue dashed line is a best fit line that is weighted by the number of projects at each age. And that simply means that the older plants with the wider confidence intervals don't have as much influence on the slope. You can see here that the slope of the best fit line is minus 1.3% per year, which is our estimate of average performance decline with age for the full sample of projects. As I mentioned earlier, we controlled for both geographic and temporal variation in irradiance through the ideal capacity factor, and we also controlled for curtailment in CalISO and ERCOT. And this graph here is simply showing how those two corrections affect the results. So in green, the uncorrected or raw data, shown there by the green triangles, has a slope of minus 1.7% per year. But once we control for irradiance through the ideal capacity factor, the slope improves to minus 1.4% per year, which is shown by the orange squares. And then finally, after also accounting for curtailment in CalISO and ERCOT, the slope improves even further to minus 1.3% per year, which is the blue circles that you see here and that I also showed you on the previous slide. So again, these results are for the entire sample, and although the low temporal resolution of the data prevents us from digging too deeply into the specific causes of performance decline, we did nevertheless use the fixed effects regression to compare performance among various subsamples of the data. And a few of those findings stood out as statistically significant. So first, we found that newer projects have declined less than older projects. And this is perhaps not surprising, given that we would expect or at least hope that PV technology and balance of system components have improved and become more reliable over time. We also found that larger projects have declined less than smaller projects. Again, perhaps not surprising if one believes that larger projects are likely to have a more rigorous operations and maintenance regimen, and that any performance problems are likely to be flagged and fixed more rapidly than they might be for a smaller project. Projects located at cooler and or less sunny sites have declined less than projects at hotter, sunnier sites, and these results are consistent with past work that shows how higher temperatures erode the efficiency of PV modules and can lead to more rapid degradation. And then finally, projects with higher DC to AC ratios have declined less. This one is also intuitive, given that a higher DC to AC ratio results in more power clipping at the inverter, which in turn can mask any degradation or performance decline that happens on the DC side of the inverter. So just to summarize, while our top line performance decline number for the entire sample was minus 1.3% per year on average, if you instead look at just those projects that most closely resemble recent builds or recent project vintages, the numbers look better. So in other words, for more recent projects that are larger with higher DC to AC ratios and that are more likely to be sited outside of the desert Southwest and in other parts of the country, the rate of performance decline appears to be somewhere less than 1% per year. But even 1% per year is more than many projects seem to be expecting, at least based on the degradation rates that are codified or embedded within their power purchase agreements. The graph here shows a histogram of expected rates of performance decline embedded within 93 PPAs totaling 7.3 gigawatts of AC capacity. And as you can see, roughly 2/3 of these contracts expect performance decline to be 0.5% per year or better, which almost makes one wonder whether these contracts are perhaps confusing system-level performance decline with module degradation. Whatever the cause, the consequences of underestimating performance decline can be very real. For example, a project that expects to achieve a 10% internal rate of return, assuming 0.5% per year performance decline, will actually earn only half as much, so just a 5% IRR, if performance actually declines by 1% per year. So it's important to keep monitoring performance over time and tracking these numbers, and also to clearly understand the difference between module level degradation and system level performance decline. And then also, of course, to make sure you're not conflating the two in your documentation. And with that, let's take a few minutes for some questions. Any questions that we can't get to or that we do not answer adequately, we can certainly try to follow up on afterwards. Email addresses for all 4 of the authors are shown here, and there's also a web link to the journal article, which is also where a recording of this webinar will be posted within a few days. So thanks for attending. Again, if you have questions, please submit them through the Q&A button. And I guess I'll ask Dev or Will at this point. Do we have any questions queued up to go right now?
Yeah, hi, Mark. And hello, everybody. This is Dev. We have a few questions here. So the first question, we'll maybe just start at the top. This is a question about multi-unit plants. Plants that have come on in phases at different dates. And so the question is, how do we deal with those plants, basically?
Yeah, so that's a good question. And what we've done is we've waited until the very last phase has come online and started operating. And the reason for that is just to make sure that we're accounting for the full output of the plant. That's kind of a conservative way to do it, but and it also costs us sample size as well as the period over which we can measure performance in some cases, because there are a few plants that have come online in 2 or 3 phases over 2 or 3 years actually. So it's not an ideal way to do it because it does eat into your sample as well as your performance period, but it seemed to be the most conservative way to do it. And I guess just related to that, I should have clarified that we count year 1 in this case, or age 1, as being the first full calendar year after the project has fully come online. So in other words, for a project that came online in, let's say, September 2016, year 1 would be 2017, and year 2 would be 2018.
Hey, Mark, and I'll just quickly chime in here. Everything you said is correct, but there is a few cases in which we could identify the megawatts that did come on stages. So there's maybe 3 or 4 projects where we just updated the size of those plants over time to make sure we adjusted the capacity factors appropriately. So when available, we tried to do some modeling of the phase-in, but as Mark mentioned, it's challenging, and usually we drop them from the sample.
Yep, that's right. Thanks, Will.
So I'll ask the next one. And this is a question about dust buildup or contamination. And the question was, did we consider those 2 issues of dust buildup in the Southwest versus other locations, or did we assume that these are cleaned?
Yeah, so we have no visibility into soiling for this analysis, and so we made no adjustment for that. And I think someone else has pointed out before that perhaps the results that we found by bifurcating the sample by average site temperature, there could be a correlation there with soiling as well. Typically an average, a site with a higher average temperature is probably one maybe that's out in the desert where rain is not as prevalent, and so there could be some conflation there with soiling as well, but that's not something that we were able to account for.
Okay, here's another question about the module versus system decline, and the question is if PPA creators are conflating module and system decline, what value for system decline would you have expected instead?
Yeah, so maybe I'll just go back to that graph here. So you can see that this is kind of a multimodal distribution, I guess, and you can see that there is a little bit of a secondary spike there at the 0.7 to 0.8% range, and I'm guessing that those PPAs are probably focusing more on system level decline. If you look back at the literature, as I said before, most of it is focused on module degradation and not system level decline. And typically, I guess a rough rule of thumb might be modules degrade at around 0.5% per year, systems maybe more at like 0.75, 0.8, 0.9% per year. So we're finding something a little bit higher than that or a little worse than that. Though again, if we look just at the more recent systems or at the subset of systems that look a lot more like recent systems, our numbers really aren't that far off with the past literature.
Great. So maybe somewhat of a similar question or follow-up on this, Mark. How would you advise today's project buyers to account for system-level degradation effects in PPA contracts going forward?
Yeah, that's a good question, and there are really kind of 2 components to this. Within your typical PPA, there'll be a performance guarantee there that's based on some combination of expected first-year production as well as subsequent performance decline over time. And so it's really a question of how those 2 things interact. Whether you're, well, let's put it this way: if you're conservative on your estimate of first-year generation, then you can probably also afford to be conservative, or I'm sorry, to be aggressive on your on your performance decline, because it's really the combination of those two things that's going to determine whether or not your system is actually living up to overall expectations and kind of passing the performance guarantee tests that are embedded within the PPA. So, you know, my guess is most developers try to be a little bit conservative, setting the first year performance decline, and I'm sorry, the first year performance numbers. And you know, I guess I would just caution against using something as low as 0.5 for system level decline. I think that's more of a module number. You know, it could be that some of the newer systems, some of the newer technology that's coming out, you know, could potentially hit those numbers, but in general, developers are going to want to be somewhat conservative when estimating these numbers.
Great. Here is a question about the difference in degradation from differing module technologies. And so the question is, did you find any difference between these technologies, such as poly or PERC or thin film?
Yeah, so unfortunately, we don't have great visibility into you know, highly resolved differences between technologies. In most cases, we do have the module manufacturer and maybe also the wattage of the module. And so from those two things, we can often kind of glean what type of module technology is being used. So we did look at you know, thin film, for example, or cadmium telluride versus silicon modules. Didn't really find a statistically significant difference there. I guess I should note that CAD-TEL makes up about, I think, maybe 20% of the projects in our sample, though more like a third of all capacity. So it's a fairly small subset of the overall sample, and we didn't really see any statistically significant differences between those two technologies. And then beyond that, I think we also looked at differences among some of the different module manufacturers, but again, couldn't find anything statistically significant there.
Great. So I'll ask the next one, and this is maybe a further clarification of the system level versus module level degradation. But the question is, did we have sufficient data to be able to exclude data points that might be heavily impacted by grid outages or other non-project related events?
Yeah, so this is one of the problems working with annual data, is that there's a lot that, you know, goes on throughout the year that we're not able to see. As I mentioned, we did attempt to correct for curtailment, which has been kind of an increasing source of outages, if you will. But beyond that, I guess all I can say is, you know, we looked at all of the data and did some, you know, quality control to kind of weed out anything that looked abnormal or fishy. But yeah, it's to some extent we were limited by the low frequency of our data. It really kind of limited what we could do in terms of looking for outages and trying to control for those. And I guess just as an add-on to that, I should mention that we are in the process of updating the sample for another year, so we'll be adding projects, I guess, that came online through 2017, so that should add another, you know, 5 gigawatts or so to the sample, and then we'll also gain another year of performance in 2019, and we hope to have results from that updated analysis out probably within a month or two, and as always, we will continue to try to improve the analysis and look for new ways that we can use the data going forward. Okay, we may have time for one more if there's one more question out there.
Yeah, we have a few more. So to people's questions we didn't get to, we will try and follow up via email. And maybe for the last question, just to go a different direction here, does this work translate at all to distributed or behind the meter installs?
I would say Only loosely. Obviously most of these, well, all of these projects are ground mounted, and most of them are using single axis tracking, which is not something that you find very often for behind the meter, or certainly not for rooftop PV. We are aware that some of the projects that declined more heavily over time, that trackers may have been behind some of that, and so I'm not sure how applicable these numbers really are to those other two sectors of the market. So I think we should probably cut it off there, and as Deb mentioned, we'll try to get back to everybody else who submitted a question that we didn't have time to answer. It's been a half hour now, so I think we'll cut it off. Thanks everyone for attending, and again, this recording will be posted within a few days on the website. Thank you very much, and have a great day.